So this is part 2 of our previous discussion. Here I want to derive the equation for lift and drag, and also I want to do a simple example where we can apply some of these concepts that we have learned. Just as a review, first of all, remember the Kara-Joukowski theorem basically states that if you have some sort of circulation, and the circulation can be in the x, y, z directions, then you're going to have a body force, okay, which we derived as equal to this. So based on this, we also derived that based on our analysis that we can assume for infinite airfoil, you cannot have any rotations in this direction. You can only have rotation about the z direction. So therefore, these two are completely equal to 0. So you're basically left with this following expression. To understand this, let's go ahead and find the cross product of these two guys. And we're going to do that now. So for this example, so we're going to know that the body force is basically nothing else than V infinite. And we're going to call this V infinite, the stream velocity, plus small v u. And if I can draw this, this is nothing else than something like this, okay, where this is your v, this is your stream velocity. Typically, your stream velocity is way bigger than v, so therefore this term can be negligible, but it does exist especially for airfoils, and we're going to learn that in the next, in topic number 9, you will see that is true. Also, well, you can see that this is equal to gamma times k. From here, then, we can do the cross product, cross times gamma, which is equal to I, j, k. And you have u, you have v infinite, v 0, 0, 0, and gamma. So if we take this, this is I times V infinite times I, and then, sorry, this is V. I eliminate this, minus J gives me V infinite times gamma, okay? So if I take this expression and I plug it back inside this expression right here, that will give you the value of your total force acting on the surface and the total acting on the body, and that will give you minus, I will be V, minus, minus, and minus, minus become plus. So this is equal to gamma I plus rho times V infinite gamma. Just note that all this is working in the infinite. We are working in, is a free stream. So this is your drag, and this is your lift. Okay. So when we talk about this drag, we are talking the drag goes in this direction, typically letter D. And your lift goes perpendicular to up, and this is lift. Okay, so basically just keep in mind what we are really trying to do. What we are trying to do is we are stopping the airfoil, we are keeping the airfoil completely fixed, and we are letting the stream velocity move. Okay, so this would be V infinite. But remember, it's the same problem if I was going to keep your air completely constant, so this is not moving. Only thing that's moving is your airplane, your airfoil is moving at the velocity v. These problems are completely identical to each other. Okay, so this is the same as this, but this is easier when we analyze airfoils. Okay. Now, before we move on, I want to fix a couple of ideas here. One of the first ideas I want to fix is that your lift is actually in general equal to this expression, and the big question is why we are using a negative sign when we got a positive sign here. So there are a couple of ways to look at this. First of all, we engineers typically use this counterclockwise. Okay, so counterclockwise gives you ds, and that will give you L is equal to minus rho V infinite gamma. And the mathematicians like to use this. I'm going to put a dash there for minus V, minus gamma. They like to use this counterclockwise. And for them, this is equal to ds. And from here, they get L is equal to rho times V times gamma. Okay, so they get it positive, we get it negative. Just be cautious on how you're taking rotation, and if you're having a positive lift or a negative lift. So now what we want to do is we want to move to one simple example to understand how some of these concepts work. Let's consider the case of a submarine that's completely immersed. So this is deep enough from here to here. And we want to determine the drag acting on the submarine moving in the Atlantic Ocean. And we want to state all the possible assumptions in this problem. Okay, so the first assumption we're going to do is we are going to assume that assumption number one, that all the properties in one are identically equal to the properties at two. Okay, so at property one and property two, these are identical properties. Number two, let's assume the fluid is ideal fluid. So fluid is ideal. There are a couple of consequences by assuming the fluid is ideal. And if you recall, for the first consequences, if it's ideal, that means it is incompressible and is inviscid. So there is incompressible, there's no shear, and the body is completely immersed in an infinite body, infinite fluid. In an infinite fluid. And the consequences of this is I can basically know what's happening if I get close to the surface, at the bottom of the surface, where there can be probably some, there could be shear involved here. So when I have a flow that does something like this, right? So here, anywhere from here to here, we can assume that this is completely constant. Okay, so that's the consequence of that. And we're going to assume that the flow is completely steady. So it's a steady flow. By steady flow, we mean that V is actually constant in our problem. We can assume that the fluid is irrotational. And also there is your circulation is zero over every possible closed circuit. Okay. So if there's no circulation, if you remember the Lambert's paradox, if no circulation, then there's absolutely no force. And if there's no force, then we basically can immediately conclude the following, that under the assumptions that we made, under these assumptions, we can state that the Lambert's principle applies. Which state that if circulation is zero, this means that your force is equal to zero, and therefore your drag in the problem that we're asking for is actually equal to zero. It's a full consequence of that. And actually, if this is zero, we can also show that your lift is also zero, although the problem didn't ask for that. So this concludes part 2 of forces on a general body.